this section's about bifurcations. So before we even talk about the mathy stuff, a bifurcation is describing a moment when things fundamentally change, right? When the solutions to a differential equation just become very different. So think about like if you have something kind of resting on the edge of a table, like you can move it a little bit, nothing's really different. You can move it a little bit more, nothing's really different. But if I keep doing this, right, at some point, the physical state of what's there is going to be fundamentally different, right? So there's a moment in time where things change, and that is called a bifurcation. Okay, so a common feature in many mathematical models when you're trying to model something in the real world is the presence of a parameter along with the variables that are involved. So parameters are quantities that don't depend on time or which is the independent variable, but they assume different values depending on the specifics of the application. So like the Malthusian model with population growth, where a population grows, its rate of growth is proportional to the size of the population. That parameter k is different for different populations. K, the constant of proportionality k, will be very different if you're studying a population of fruit flies than if you're studying a population of humans, right? So we call it a parameter. It doesn't depend on time, but it varies depending on the situation. So our goal in this class is going to be to study how the solutions to a differential equation change as that parameter changes. And it's often a really important question to answer if you're using a differential equation to model a real-world situation. All right, so let's look at a family of differential equations. dy dt is y squared minus 4y plus mu. Okay, so mu is our parameter. That's the thing that changes based on the situation we're modeling. And our goal is going to see what the solutions to the differential equations look like and how they depend on mu. So we're going to start by investigating parabolas defined by the right-hand side of the differential equation, f sub mu of y. So we're just going to look at that right-hand side, the derivative, as a function, see what it looks like. So f sub 0 of y would be make the mu a 0, so that would just be y squared minus 4y. So if mu were 0, that last term just goes away, and when you graph it, it looks like this. All right, so how many places is the derivative 0 in that parabola? 2. Crosses the x-axis twice, right here and here, which means because this thing is the derivative that I've just graphed, there are 2 equilibrium solutions, right? But will there always be 2 equilibrium solutions for every value of mu? No, because what does mu do? How do the graphs of parabolas y squared minus 4y plus mu relate to the graph we just drew? It's going to shift it up and down. That plus mu is just going to be a vertical shift. So the bifurcation value is going to be the point, the mu value that fundamentally changes things, right? If I shift this up by 1 unit, right? My parabola is going to look something like this, right? Shift it up a little bit. There's still 2 equilibrium solutions. Shift it up a little bit more. There's still 2 equilibrium solutions. But there's some value of mu where I've shifted this up just enough so that I have fundamentally changed things, and that now there's only 1 equilibrium solution. And after that point, there will be none, right? It won't cross the x-axis at all. So there's some value of mu where the solutions, what the solutions look like fundamentally changes. Goes from 2 equilibrium solutions to 1 and to none. So this place where there's 1, that's sort of like a boundary case, going from 2 to none. So we have to figure out how to find what is the value of mu where this happens, right? So that's the bifurcation value. So we drew the one that has its vertex tangent to the horizontal axis. That's the first pink parabola, right? So how can I find that value of mu? How do I figure out exactly how much to shift that parabola up by so that I get exactly tangent to the x-axis? Make what equal to 2?
You want to line up between 0 and 4.
Uh-huh.
There's only one.
Right, so I know that no matter what mu is, right, the x value here is 2, right? The vertex always is going to be at an x value of 2. Right, so say it one more time. What do you want me to do? Make the derivative. Yeah, I definitely have to do something with the derivative of that parabola. Right, okay, yeah, so the y coordinate of this minimum value, right? What is this point? You can use the derivative too, but I'll do it both ways. So this point right here is at 2, -4. I know the equation of that parabola, right? And so I can find its vertex. It's at 2, -4. So how much do I have to move that up by to land right on the x-axis? 4, right? So I need to do a vertical shift by 4. That's the mu value where things fundamentally change. Mu equals 4. But it is also true that the function value and the derivative value have to both be 0 at the point at 2, right? So f of 2 has to equal 0 because I want to be on the x-axis, and f prime of 2 has to equal 0 because I need that. It needs to be the minimum that's on the x-axis. So we call that bifurcation value 4. Like in general, in this case it's 4, but in general we call it b for the bifurcation value. That's where interesting things happen. That's where the the fundamental way that the solutions look changes at that value of the parameter. Okay. So let's stop there. I don't want to get too much into it without you being able to take notes.